Introduction. Welcome to Module 2 of our lecture series on reservoir engineering. In Module 1, we explored the fundamentals of petroleum reservoir engineering, including the physical properties of reservoir rocks and fluids, fluid flow through porous media, and reservoir drive mechanisms. In this second module, we'll focus on deeper concepts related to fluid analysis and behavior, including phase behavior, equilibrium constants, sampling for PVT analysis, and methods used to evaluate and interpret reservoir fluid properties. These concepts form the analytical backbone of reservoir characterization and development planning. Section 1: Basic concept of phase behavior in hydrocarbon systems. Understanding phase behavior is essential for predicting how hydrocarbons will behave under different temperature and pressure conditions in the reservoir and at the surface. 1.1 Definition of phase behavior. Phase behavior refers to the changes that occur in a hydrocarbon system when subjected to varying pressure and temperature conditions. It involves the transition of hydrocarbon mixtures between gas, liquid, and sometimes solid phases. These transitions are not random, they follow predictable paths and are mapped using phase diagrams. Such diagrams show phase boundaries, critical points, and regions where multiple phases coexist. 1.2 Importance in reservoir engineering. Knowledge of phase behavior is crucial for reservoir performance forecasting, surface facility design, selection of enhanced oil recovery techniques, reservoir simulation models. An accurate phase behavior analysis allows engineers to optimize production strategies and avoid operational issues such as hydrate formation, asphaltene precipitation, and retrograde condensation. 1.3 Single, binary, and multi-component systems. Hydrocarbon systems can be categorized based on the number of chemical components they contain. Single-component systems, these contain only one type of molecule, such as pure methane. Their behavior is relatively simple and involves clear phase changes between liquid and vapor as pressure and temperature vary. Binary systems, these involve two components, such as methane and hexane. Binary systems are often used for teaching and visualizing more complex interactions like phase splitting and critical mixing points. Multi-component systems, real reservoir fluids typically fall into this category. They contain a variety of hydrocarbons ranging from light gases to heavy oils, and their behavior is more complex and modeled using equations of state. In multi-component systems, interactions between different hydrocarbon molecules influence how and when phases change, making laboratory analysis and simulation essential. Section 2: Equilibrium constants and their application. The next important concept in reservoir fluid characterization is the equilibrium constant. 2.1 What is an equilibrium constant? In phase behavior studies, the equilibrium constant, often referred to as the K-value, expresses the ratio of the concentration of a component in the vapor phase to that in the liquid phase when the system is in equilibrium. In simple terms, it describes how a component distributes itself between gas and liquid phases. A K-value greater than 1 means a component prefers the vapor phase, while a value less than 1 indicates a preference for the liquid phase. 2.2 Application in reservoir engineering. Equilibrium constants are used extensively in phase behavior modeling and simulation. They are especially useful in flash calculations, where a fluid is separated into gas and liquid. Reservoir compositional simulations. Design of separation and fractionation units at surface facilities. Because K-values depend on pressure, temperature, and composition, they are often determined experimentally or estimated using correlations and equations of state. 2.3 Limitations and challenges. One of the main challenges with equilibrium constants is their variation across different reservoir conditions. This necessitates the use of complex numerical models and lab experiments to generate reliable data. Furthermore, at high pressures or in the presence of heavy hydrocarbons, equilibrium becomes more difficult to predict accurately, necessitating more advanced equations of state and phase behavior software. Section 3: Sampling for PVT analysis. Sampling is a vital part of understanding reservoir fluids. Without representative samples, All analyses and decisions based on fluid behavior may be flawed. 3.1 Purpose of PVT sampling. PVT, which stands for pressure volume temperature, refers to the laboratory analysis of reservoir fluids to determine their physical and thermodynamic properties under reservoir and surface conditions. Proper sampling provides the foundation for reserve estimation, recovery strategy planning, equipment design, enhanced oil recovery assessments. 3.2 Types of reservoir fluids sampled. The types of samples collected include bottom hole oil samples, bottom hole gas samples, separator samples from surface separators, recombined samples from separator streams. Each sample type has its own use cases and associated limitations. 3.3 Sampling techniques. There are two main methods of obtaining representative samples.